Welcome back to ME 760 Engineering Analysis 1. So last time we were just discussing the how to do the matrix diagonalization, and we stated that we will be discussing two cases or two situations. The first situation where the eigenvalues for the matrix are distinct and they are not degenerate. And the second case where the eigenvalues will be distinct. And we clearly stated why we are doing the matrix diagonalization and what are the benefits from diagonalizing a matrix. And we stated last time that maybe when you try to solve a system of linear algebraic equation, you will end up with a very large matrix. It's a sparse matrix, let's say 1,000,000 by 1,000,000 or something like this elements. So you want to reduce this matrix to a form that it will be easy to or trivially solve the system of equations. And if you will be able to transform the matrix A to another matrix B which is similar to A, and it has similar properties using the similarity transformation that we described or discussed a couple of lectures ago, you will be able to transform the matrix to a diagonal matrix, and in this case it will be an easy job that you will be able to figure out what are the vector values of vector x, which is the solution for the linear algebraic equation. So again, last time we discussed the non-degenerate case. Now let's go ahead and discuss the degenerate case. So in the degenerate case, assume that we have a matrix A equal to 1, 1, minus 1, and a 3. So what we did last time is, first of all, we have to figure out what are the eigenvalues, excuse me, eigenvalues of the matrix A. So this was the first step. So how to figure out the eigenvalues is to solve the characteristic equation A minus lambda I equal to 0, and in this case you will be able to get the eigenvalues for this equation. So again, now what is the characteristic equation? It will be 1 minus lambda, 1 minus 1, and 3 minus lambda. So to get the determinant, in this case will be the determinant will be 1 minus lambda multiplied by 3 minus lambda plus 1. If you rearrange, and this will be equal to 0. If you arrange this will give you lambda square minus 4 lambda plus 4 is equal to 0. And now you can decompose it to lambda minus 2 and lambda minus 2. So what are the values for the eigenvalues here? Lambda 1 is equal to 2, and lambda 2 is equal to what? 2 also. So they are identical eigenvalues. So if the eigenvalues are identical, we call this case is what? Degenerate, and the eigenvalues are deficient. So this is a degenerate case. So let's look for, the second thing is to look for the eigenvectors. And what are the eigenvectors? We have to solve AU equal to lambda U. And again, it's 1, 1, minus 1, and 3. And then the components of the eigenvector, we will call it x1 and x2. And the eigenvalue here, the second, let's say the first eigenvalue will be 2, and the second eigenvalue will be 2. So we'll use 2 and x1, x2. So for the two situation or two cases, lambda 1 and lambda 2 are equal, so it will give me only one equation. So if we solve this equation, you will notice that x1 plus x2 is just equal to 2x1, and negative x1 plus 3x2 equal to 2x2. And this will give you the following set of equations. This will give you negative x1 plus x2 is equal to 0, and negative x1 again plus x2 is equal to 0. So same equation. So it's two equations, but they are identical or linearly dependent. So one is multiplied by the other. One is the other multiplied by one. So in this case, I will have only one eigenvector, which is u1, and the solution for the u1 will be just 1 and 1. Now, if you want to normalize this vector, you will divide by what? Huh? Square root of 2, which is 1 square plus 1 square under the square root, so it will be the square root of 2. So now we have only one eigenvector now, so I cannot have in two-dimensional vector space, I cannot have a basis which is just composed of one vector. So I have to have another vector for the linear vector space. So I do not have the eigenvalues. As we all know, if we have a square matrix like this, and now we get the eigenvalues and eigenvectors, the eigenvectors for a non-degenerate case will form a basis for the linear vector space. And we saw this last time, that u1 and u2 form a basis for a linear vector space. And we showed that last time the completeness, if they form a linear vector space or not, we assume that we have another vector, new vector, which is composed of what? Alpha and beta. And we look at the value of alpha and beta, how to compose the new vector as a linear combination of u1 and u2. But here, I have only u1. So what should I do? In this case, we will look for another vector, and we call it auxiliary vector. Auxiliary vector to form a set of bases. So let's choose u2 equal to AB, where A does not equal to B. Why? Because if A equal to B, in this case you will be able to take A outside or B outside. So it will be A multiplied by what? 1 and 1. And U1 is what? 1 and 1. So the second vector will be a linear combination of the first vector. So I cannot form a basis for the vector space. So in this case, I have to take A and B, and A is not equal to B, so that I will have two linearly independent vectors which can form a basis. So now, let's look for the completeness of these two vectors. So we can expand any vector like before, alpha and beta, in terms of those two vectors. So we'll say that this is some constant C multiplied by vector U1 plus another vector D, another constant D multiplied by U2. So what's U1? 1 and 1. And what's U2? A and B. Then you can get alpha equal to C plus dA, and beta equal to C plus dB. And again, you will be able to do exactly like last time. You will figure out what are the values for D and what's the value for C. So B beta minus alpha divided by B minus A. And what's C? Is B alpha minus beta A divided by B minus A. Again, if you look here, if B equal to A, which we already prevent in this case, what will happen here? B minus A will be equal to what? 0, and anything divided by 0 is infinity. So you will not be able to get any values for D and C that can give you a linear combination from U1 and U2 to form a new vector. So they are not complete if A equal to B. Now, the last step is to be able to reduce the matrix reduce the matrix to the Jordanian or Jordan canonical form. And Jordan canonical form is just the diagonalization that we talked about last time. So how we will form the transformation matrix X? Last time we stated that the transformation matrix is composed of what? U1 and U2. So this will be U1 and U2. So how you will form it? You'll just put 1, 1, and A and B. So what's S minus 1? To get S minus 1, you have to divide by the determinant and then get the what? The cofactor matrix. So what's the determinant here? B minus A. So this is B minus A. This is B minus A. And the cofactors will be what? We'll take this. So this will be what? B. And then we'll take the other one to 1. So the other one will be what? Minus A. And then we will get this one. This one will be what? Minus 1. And then we will get this one. And this one will give us what? 1. So it is B minus A minus 1 and 1. So if you do this and you do all the multiplication of 1 over B minus A, you will notice that you will end up with 1 over B minus A. Of course, this is multiplied by, okay, no. This is just this one. You made a mistake here. So if you multiply now S minus 1 with S to make a check, just a check. So what's the multiplication for S minus 1 and S? Will be equal to what? 1 over B minus A multiplied by B minus A minus 1 and 1. And what's S? 1A and then 1B. So if you do this, you will end up with B multiplied by A, B minus A, B multiplied by 1 is B minus A. So this is B minus A, and then B multiplied by A is BA, and then this is minus AB. So minus AB, and then minus 1 plus 1 is what? Is 0. And this one will give you what? Will give you B minus A. So B minus A, and you have here B minus A, B minus A is 0 also. So BA and AB is 0. So this will give you, if you multiply it here by 1 over B minus A, this will give you what? 1, 0, 0, 1, which is the identity matrix. So yes, S minus 1 and S minus 1 is indeed the inverse of the S matrix. Now, how we will apply the similarity transformation? So it will be S minus 1 AS, and what's S minus 1 now? 1 over B minus A, B A minus 1 1, and the matrix is 1 1 minus 1 3, and then 1 A 1 B. If you do this, you will end up with 2 B minus A 0 and 2. So what's this? What? The eigenvalues. So eigenvalue 1 and eigenvalue 2 are identical. 1 and 2 is equal to 2. But we got an extra term here because of the eigenvalue deficiency. We got this extra term. So last time, when we do not have deficient case, and the eigenvalues are what? Are distinct, non-degenerate. We got what? Diagonal matrix was what? With 2 and 2 and 0 and 0. But for the degenerate case, we got what? We got another matrix, and it has the diagonal is the eigenvectors, but the off diagonal here, we got a new element in the matrix here. So let's assume, for example, that we will choose A equal to 1 and B equal to 2. So S minus 1 A S will give me 2 1 0 2. So do you think that U2, the auxiliary vector that we choose, will form an eigenvector for the matrix A? We knew that U1 form an eigenvector. Yes, because we deduce what's U1. And U1 is equal to what? 1 1. So if you multiply A by 1 1, this will give you 2 1 1. You will notice that this equation holds. Okay, but what about U2? U2 was not deduced from this formula. So let's now look at A U2 is equal to what? 1 1 minus 1 and 3 and 1 and 2. We picked up A equal to 1 and B equal to 2. So let's see how this will end up. So this gives us 3 and 5. And what's 3 and 5? I can represent 3 and 5 as equal to 1 1, which is equal to what? U1 plus 2 multiplied by 1 and 2. And this will give me what? U1 plus lambda multiplied by what? By U2. So it's not an eigenvalue problem, because eigenvalue problem means that A U2 equal to lambda U2, but you get an extra U1 here. Okay, guys? So because of the deficiency of the eigenvalues or the degeneracy of the eigenvalues, we have to pick up, let's say if this is 3 by 3, how many eigenvalues we will have? Let's say maybe 3, because you will have third order equation, polynomial in lambda. So we'll have 3. If 2 of them are degenerate, so I have to look for what? I will get 1 eigenvector, and I have to look for 2 auxiliary what? 2 auxiliary vectors, and so on. So now the auxiliary vector form a new vector that's not an eigenvector of the matrix A. So did you understand now the powerful of the technique for the Jordan technique for diagonalizing a matrix? Okay, now we will diverge a little bit from the book. So what I will be talking about today is not in the book. And we will be talking about iterative techniques for solving the matrices. And you will find online a handout written by Professor Schultz about how to use the iterative technique in solving system of linear equations. More specifically, when you will have a very large matrices formed from the system of linear equations. So if you have let's say, if you assume that we have a system of linear equations and there is a matrix that is million by million, million element by million element, or a billion element by billion element, we will not be able to solve it using the Gaussian elimination technique, because you have to do lots of operations, and in this case you will have something like billion by billion operation that you have to do in order to solve and transform it from the normal matrix, for example, and use Gaussian elimination to get the vector x, which is the unknown in this case that you are looking for. So in this case, we will not be able to use the Gaussian elimination technique, and we have to look for another technique to be able to solve the system of linear equations. Usually, this technique will be just iterative or iteration techniques of solving the matrices or system of linear algebraic equations. And the first thing is to start by defining what do we mean if we want to go and define how to solve the system of linear equation using iterative techniques. We have to define some of the parameters of this technique. And the first thing we have to define is what we call a spectral radius. So this is not in text. So that you would be aware, you have to go and read this part from the online material or online chapter that Dr. Schultz wrote it before. So how to find, let's say, if we want to find the largest eigenvalue for a matrix, how to find the largest eigenvalue for the matrix. And the definition of the spectral radius is just the largest eigenvalue for a matrix. So we will define and from this lecture on, we will be able to see the importance of the spectral radius and how the spectral radius is one of the great ingredients of iteratively solving a system of linear algebraic equations. So just we will focus on defining the spectral radius during this lecture here. So we will define the spectral radius of a matrix A as mu of A, and it is equal to the maximum of I of all the lambda I. So it is the maximum of all lambdas of the eigenvalues of the matrix. So let's assume for the last example, for the non-degenerate case, we have two values for lambda. Do you remember? For the last lecture, it was what? 4 and 2. So what will be the spectral radius for the matrix? 4. It's the largest value, and this is what we will see here. So how to calculate the spectral radius here? We usually use a method called the Bauer method. And this is a very powerful technique to figure out what is the spectral radius. So usually you start, for example, by a first guess for a vector x. Okay? So we will have a vector x, and this vector x, we will give it an initial guess. So let's say in two-dimensional case, the eigenvalues were 4 and 2, and this is what we will be seeing in a minute. And then we have 1 and 1. I think we have 3 and 1 for the eigenvectors. So we will assume something like 5 and 2 or 6 and 2 or whatever as the first guess for the initial vector x superscript 0 between the brackets, meaning that this is the first guess for vector x. And then in order to get the spectral radius of a matrix, is all what you want to do is, this is the maximum of lambda I, and all what you want to do is just take the limit when n goes to infinity, and we'll prove it right now, of the mod x after nth iteration divided by x after n minus 1 iterations, and this is the mod of x. How we prove this? This will be the next step. This is just the power method for calculating the spectral radius for a matrix. Again, the spectral radius is the largest value for the eigenvector, and next lecture or the lecture before, we will be able to show that the spectral radius, in order to be able to solve a linear system of algebraic equation, and you have a very large sparse matrix, for example, in order to be able to solve it using iterative technique, you have to have, the condition is you have to have the spectral radius less than 1. So mu of A is less than 1 is a condition, necessary condition to solve linear systems using iterative technique. So we want to figure out what's mu of A now. So let's give the proof for the power method here. So we will assume that the eigenvalues are not degenerate. So no degenerate eigenvalues, meaning there is no deficient eigenvalues. Of course, in the case that there is also a degeneracy in the eigenvalues, the same method will work out, but we are not going to give the proof here. Just we'll assume from the beginning that we do not have any degeneracy in the eigenvalues, and let's work things out. So this is the first guess of the vector, for example, of interest x. We can write or expand it here in terms of the eigenvalues of the matrix AI, UI, where UI are the eigenvectors of the matrix A. So those are the eigenvectors of A. And I goes from 1 to n. And what's the eigenvalue equation? It's A U equal to lambda U, or we call it AUI equal to lambda I UI. So whenever you substitute with the ith eigenvector in this equation with the corresponding ith eigenvalue, this equation will hold. So for the two-dimensional case, we have what? U1 and U2. Yes, for the non-degenerate case, U1 and U2, and both are eigenvalues. So if you multiply A by U1, this will give you lambda 1 U1, and A U2, this will give you lambda 2 U2. So this will hold. Now, do you have any questions? So we will assume that lambda 1 is the largest value for all lambdas, for all lambda I. So lambda 1, the initial eigenvalue, will be the largest. So after you do nth iteration, so x of n will be equal to what? The matrix A multiplied by xn minus 1. And what's xn minus 1? xn minus 1, it will be just a multiplied by xn minus 2. And what's xn minus 2? It's a xn minus 3, and so on, until you finally reach to a x0. So this will give us what? an x initial. So the vector x that you proposed at the very early beginning was the initial value x of 0. If you multiplied with a to the power of n, the matrix a to the power of n will give you the final iteration, the final value for the vector x after nth iteration. So now I can substitute with an, and what's an? And x0. What's an? So this is equal to 1 to n, and I can say that this is equal to an multiplied by ui. Why? Because x0, the first initial value for the vector x, is just equal to the summation from I equal to 1 to n. I can represent the vector x as a linear combination of the eigenvectors. Yes, any vector x. I will have the eigenvectors, let's say in the two-dimensional case, I have u1 and u2. If you remember last time when we looked for the completeness of the solution, we said any vector alpha and beta can be written as a linear combination of u1 and u2. Yes? So let's assume that our vector alpha, the vector that has components alpha and beta, is the vector x. Okay, guys? And we will give it initial value alpha naught and beta naught. So this would be x of 0. So I give the components of the vector an initial value. And this is the vector here. Now, I have to find out after nth iteration what will be the new vector x. So after nth iteration, the vector x, we proved that it will be the matrix A raised to the power of n multiplied by the initial value, the initial guess. And the initial guess is just given by this equation here. So this would be an multiplied by ui. So what will happen if you have large value of n, and this is equal to, this one will be equal to summation from I equal to 1 to n, and what's the a to the power of n? Is lambda I to the power of what? To the power of n ui, because this is just an eigenvalue problem. Yes, guys? So let's a lambda au equal to lambda u. Okay? au equal to lambda u. So if you assume that lambda u is another vector, eigenvector, so a, if you apply over lambda u, this will give you what? Let's say that this is a new vector here. So a applied over au equal to lambda applied over lambda u. So this will give you what? A square u equal to lambda square u. And you can do this n times. So an applied over u will be equal to what? Lambda n applied over u. So we'll do here. So a to the power of n lambda ui will be lambda I to the power of n multiplied by ui. But we assumed from the early beginning that lambda 1 is the largest value. Let's assume that lambda is less than 1. Okay? So whenever you increase go up in n or increase n up to, let's say, up to n values. What will be the largest component here? So let's say that lambda is 0.5. The eigenvalues are less than 1, let's say. And the largest values of the eigenvalues are 0.9. So you have 0.03, 0.6, 0.7, and then 0.9, for example. When you sum here and you go here, what will be the most dominant part? The largest eigenvalue. Because if you have lambda, the largest one, lambda is 0.9. So let's say lambda square is what? 0.82. But if you have a lambda equal to 0.3, what's lambda square? 0.09. So you have 0.82 and 0.09. Then make it lambda to the power of 3, lambda cube. So the largest fraction will dominate. Yes, guys? And the lowest fraction will be gone. After a couple of expansion, couple of raising this to higher power, will be gone. So at large values for n, usually you will have a1, lambda 1, u1 is the most dominant. Is the most dominant term. So this is the most dominant term. Now, so what will be the amplitude or mod of x? What's the mod of x? xn? If xn is given by xn is given by a1 lambda 1 to the power of n u1, what's the modulus of this? The modulus is what? Is a1, and because a1 is just a number, so I write the modulus like this, and lambda 1 also a number, I write the modulus like this. But for the vector u1, this is the modulus of the vector u1. Yes, guys? Okay, and what's the modulus of n minus 1? This would be what? a1 modulus of lambda to the power of n minus 1 and u1 again. Yes? Do you agree, guys, or do you have any question? I do not want to leave the lecture and somebody will ask, oh, why you did this or why you did that. This is just, we started with a first guess for the vector x, and then we get the second guess, which is x1. Then we get the third guess, x3, and x4, and x5, and x7, up to x100, let's say. And x100, which is xn in this case. And we showed that xn, for large values of lambda, if lambda, let's say, is less than 1, for large values of lambda, the first term, or the largest lambda, will be the dominant term. Okay, now we got the modulus of the vector x n after nth iteration, and the modulus of the vector x after nth minus 1 iteration. So it will be the modulus after n iteration and the modulus in the iteration just before it. And we notice that those will give me this too. So if you just divide the modulus after nth iteration over the modulus in the just iteration before it, you will notice that this will give you what? A1 will cancel, and U1 will cancel, and you will end up with what? Lambda 1. So this means that the spectral radius, which is what we assume from the beginning that it is lambda 1, is equal to what? Limit with n goes to infinity, okay, of the modulus of what? Xn divided by the modulus of what? Xn minus 1. And this is the proof of the theory of the spectral Bauer method to get the spectral radius of a matrix. So let's take an example. Let's show an example here. Yes.
In that place, it should be largest value of n, or when
For a large, I said for a large value of n. When you increase n, when you expand the summation here, it will be a1, a1 lambda 1, u1, then a2 lambda 2, a2, then a3 lambda 3, and so on. So for the because n here is not, you are not running over n. You are not running over n. You are running over what? Over I. So this will be what? This will be a1 lambda 1 to the power of n u1 plus a2 lambda 2 to the power of n also u2 plus a3 lambda 3 to the power of n u3, and so on until you get an lambda n to the power of n un.
So is
So-
the n in your index on your summation the same n as your exponent?
If it's in the capital, I will make it in the capital. Let's say in capital, not to confuse. N capital here is the number of eigenvectors. Yes? Number of eigenvectors. But N here is what? Number of what? Iteration. Okay, guys? So let's take an example. It will be very easy and very obvious what we are doing here. Do you remember the example that we discussed a couple of lectures ago? I think it was actually last lecture, 1, 3, and 1, 5. And we stated that this one has degeneracy or non-degenerate eigenvalues. It was not degenerate. So lambda 1 was equal to what? 4. And lambda 2 is equal to what? So a u1, if you remember, was equal to what? 1 and 1. And u2 was equal to 2 and 1. 2 and 1, no, it was equal to 3 and 1. 3 and 1. Okay, guys? So the formula again, x to the power of n would be equal to a x after the iteration n minus 1. So let's pick the value for x, initial value, initial guess. Let's assume that x initial will be something like 2 and 1. Okay, guys? So we have the first eigenvector, the second eigenvector, and we have an x initial equal to 2 and 1, the components 2 and 1. So let's apply now the power method. X after one iteration will be equal to what? A multiplied by what? X at what? X at 0. So what's A? 1, 3, 1, 5. And what's x at 0? 2 and 1. So if you multiply this, 1 by 2 is 2, plus 3 is what? Is 5. And 1 by 2 is 2, plus 5. Actually, there is
A is 1, 3, minus
there is
1,
minus 1. Minus 1. So it will be minus 2 plus 5. It will give you what? 3. So we got what? 5 and 3. So this is x1. Now let's look for the modulus of x1. So what's the modulus of x1? The modulus of x1 will be just 5 square plus 3 square under the square root. So it will be 25 plus what? Plus 9. And this will give you 5.83. Let's look for x2. x2 is just equal to a multiplied by what? By x at iteration 1. And this is just, if you multiply again, a is just the same matrix. You will multiply it by the new vector. Now the new vector is what? 5 and 3. This will give you 14 and 10. If you calculate x2 the modulus of x2, you will get 17.20. 17 point what? 0.20. If you divide x2 modulus by x1 modulus, you will end up getting 2.95. Okay, guys? Then you will get, do again x3, x4, x5, x6, x7, same way. I have them all here, so let's assume that I will get x9. So x9 will be what? A multiplied by x what? Multiplied by x8. If you do this, you will get x9 equal to this matrix, 1, 3, 1, 8, 4, 0, and 1, 3, 1, 3, 2, 8. Very large numbers here. And what's x, the modulus of x9? The modulus of x9 will be 186,088. If you calculate x10, you will get x10 equal to 525,824, and then 524,800, and then you will get x10, the modulus of x10. This will give you 742,903. If you divide x10 by x9, you will get the following number. Divide x10, the 10th iteration, by x9, you will get 3.992. So what does it mean? When n increases, the number of iteration increases, what happens is we are approaching what? 4. What's 4? The first eigenvalue. So this is the power method. But beware that while you are doing this, those numbers in the vector now increases a lot. So you started with what? The first initial guess will start with what? 2 and 1. And we end up with what? 500,000. So you have to figure out a way in order to renormalize those two so that they will be smaller. Let's say you normalize. What do you mean by normalize? You divide here by 500,000 or by a million. So you divide here by a million, divide here by a million. You did not do anything because the ratio between x10 and x9, this normalization factor will go out and you will still obtain the same what? The same value. So your normalization, you use normalization in order to do what? In order to, if it is the value itself is over, you will end up in over or underflow. So overflow for your computer, for example, if those numbers will grow up indefinitely and you will not have enough memory to hold up the numbers here, so you have to normalize, or you will go in the other direction. You will go 10 to the power of minus 15, 10 to the power of minus 30, 10 to the power of minus 40, and so on. So you have to do normalization. But this technique shows you now how we get the what? The spectral radius of a matrix. So in order to get the spectral radius of a matrix, what we should do now? Get get the matrix of interest, and then once you get the matrix of interest, for example, you will just pick up a vector, any vector, for example, x. Yes, and then multiply this vector x, put an initial value, multiply it by the matrix, and then get the second what? The first guess after the iteration. Then take the first guess, multiply it by the same matrix, get the second guess, and so on, until you will see convergence for the ratio between x1 and what? xn and xn minus 1. So what happened? That if you will notice that we picked up for x of 0, the initial guess, 2 and 1. If we picked up, let's say, 2 and 1, is a linear combination between what? Between U1 and U2. We picked up something between U1 and U2. If we picked up x of 0 to be 3 and 1, this means that x of 0 is what? It's just what? It's just U1 alone. So you will note that x1 will be 6 and 2. x2 will be something like 12 and 4. And x3 will be something like 24 and 8, and so on. So you will go on. So x0, if you write it in terms of the two eigenvectors, would be a u1 plus a2 u2. But a1 is equal to what? 0, because the first eigenvector is what? 1 and 1, and the second eigenvector is 3 and 1. So this will be 0 plus a2 multiplied by u2. So only you have one eigen what? Vector. So you do not have the first eigenvector. So you do not expect to get the eigenvalue, which is u1 lambda 1. Lambda 1 was corresponding to what? Corresponds to u1, and it was 4, yes? But lambda 2 is 2 and correspond to what? u2. So you do not expect that you will end up getting the correct value for lambda in this case, if you have your initial guess does not have a linear combination of this. But usually for computers, because of the rounding errors, you will end up that you will build up something here. If you will pick up your x1 and x0, x1, when you calculate x1, it will have some rounding for the numbers, so you will end up with little bit of what? Of u1 here. Then this build up will build up after iteration, and then you will get at the end, maybe you will reach to lambda 1, which is 4. So I will stop here and continue next time.